Welcome back to The Explainer. Today, we're putting on our detective hats to crack a really cool two-part linear algebra mystery. Now, it might look like a bunch of abstract math on the surface, but what we're really doing is hunting for that one single hidden rule that makes an entire system just click into place. So, let's get started.
You know, every good mystery needs a scene of the crime. For us, that's a vector space we'll call V, and inside we have our three main characters, or maybe we should call them suspects, these subspaces, W, W1, and W2. Our mission is to figure out exactly how these three are connected.
And here they are, our first set of clues. These equations lay out the relationships between our suspects. Now, that little circle plus symbol, that means direct sum, which is a really specific way of putting spaces together. It tells us they build up the whole space V, but they only overlap in the tiniest way possible. It's kind of like two puzzle pieces that fit together perfectly, with no jagged edges hanging over. These clues right here, they're the bedrock of our whole investigation.
So this brings us to the central question, the real heart of the mystery. From our clues, we already know W1 and W2 can add up to create the whole space, but can they do it perfectly? Can they form a direct sum? In other words, is there some hidden condition, some rule, that forces them to fit together without any extra, messy overlap? That's what we're here to find.
Okay, to crack this thing, we have to think like detectives. And every good detective has their toolkit, right? Well, we're about to bust out one of the most powerful tools in all of linear algebra to follow this trail of evidence.
And here it is. This is our magnifying glass, the dimension formula. Now, dimension is really just a way of talking about the number of independent directions in a space. And this formula, well, it's so powerful because it connects the sizes of our individual subspaces with the size of their overlap and the size of the space they create together. This formula is the absolute key to cracking this case.
The mystery is asking for an if and only if condition. Now that means we need a two-way proof. It's kind of like checking an alibi from both sides, right? The story has to make sense forwards and backwards. So first, let's assume our goal is true. Let's pretend we already know that V is a direct sum of W1 and W2 and see where that logic leads us.
Okay, let's follow the chain of logic. If we assume V is a direct sum of W1 and W2, then by definition, the only thing they have in common is the zero vector. So the dimension of that intersection has to be 0. And once we plug that little 0 into our dimension formula, along with the other clues we have, the whole equation starts to simplify, and it points us right to a single, unavoidable conclusion.
And there it is. The logic reveals this simple, almost beautiful condition. The dimension of the whole space, V, has to be exactly double the dimension of that common subspace, W. This is the secret rule we've been looking for. But wait, we have to check the alibi from the other direction, remember? So now let's assume our newfound rule is true. We'll start with the idea that the dimension of V is double the dimension of W. Let's plug that back into our formula and see if it forces W1 and W2 to snap into a perfect direct sum.
And it works. It's perfect. Starting with our condition forces the dimension of the intersection to become 0, which, by definition, means they must form a direct sum. The logic holds up both ways. The two statements are basically the same thing. Case closed on part 1.
So we've solved the subspace mystery, but hey, no time to celebrate because a brand new file just landed on our desk. This time, our puzzle is a matrix whose whole identity seems to shift and change based on a couple of hidden variables.
All right, meet our new person of interest, the matrix AT. As you can see, its entries aren't fixed. They depend on these two parameters, A and T. You can think of it like an unstable structure, where its properties can just completely change depending on what those values are.
Now, we've just received a very critical piece of intelligence. We've been told that for some specific value of T, this matrix has a massive structural failure. Its rank collapses all the way down to 1. Our first job is to use this clue to figure out the hidden value of A that even makes this kind of collapse possible.
So what does a rank of 1 actually mean for a matrix? Well, it means it's lost almost all of its complexity. All 3 of its rows have become completely dependent on each other. In fact, it's even simpler than that. They all become direct multiples of one another. They're all just pointing in the exact same direction.
This whole idea of proportionality, that's our way in. If the rows are all multiples, we can just compare them, column by column. So look at the third column. For one row to be a multiple of the other,
2 has to be some multiple of 2. Well, that forces our multiplier to be exactly 1. Now that we know that, look at the second column. It tells us that 2 has to equal t minus 4, which means t has to be 6. And with those two secrets out, the first column has nowhere to hide. It just hands us the value of a. And there you have it. The hidden parameter a has to be 2. It's the only value that sets the stage for this kind of dramatic structural failure in our matrix.
Okay, with a unmasked, we can plug that value of 2 into our matrix and get ready for the final piece of the puzzle. The stage is set.
So we know how to make the rank collapse all the way to 1, but that's not what we're looking for now. We're looking for a partial collapse. We need to find the one specific value of t that makes this matrix's rank exactly 2, not 3 and not 1, exactly 2.
For this final hunt, we've got another classic tool from the detective's toolkit, the determinant. See, for a square matrix, anytime its rank drops below its full size, in this case 3, its determinant has to be 0. And that is huge because it gives us an equation we can solve to find our potential suspects for t.
So we calculate the determinant, we set it to 0, and the math spits out a very short list of suspects. T can only be 6 or -2. That's it. Now all we have to do is interrogate each one and see which one fits the crime.
Well, we can cross one suspect off our list right away. We already figured out from our earlier work that when t is 6, the matrix doesn't just dip to rank 2, it collapses all the way down to rank 1. So that's not our guy. That leaves just one possibility. T equals -2. And when we plug that value in and take a look,
we get a rank of exactly 2. The case is closed. The one and only value of t that gives us a rank of exactly 2 is -2.
So, let's step back. We've just solved two pretty different mysteries, right? One was this abstract proof about the deep structure of vector spaces, and the other was a very concrete number-crunching puzzle about a shifty matrix. So, what's the connection? What's the big takeaway here?
What we've really seen today are two sides of the exact same coin. In the first mystery, the perfect alignment of these abstract spaces all came down to a single, simple relationship between their dimensions. In the second, a matrix's entire structural integrity hinged on one specific value for a hidden parameter. And that's a really powerful idea, that so many complex systems, in math and everywhere else, are often governed by one simple hidden rule. The trick, as we saw today, is just knowing where and how to look for it.